Okay, let's begin. This video deals with something called the Gaussian distribution. The Gaussian distribution is given importance here about 3 of 4 stars. It's not clear that you might have a question that directly addresses this on a standardized type exam. However, things that you talk about in analytical chemistry class are directly rooted in this Gaussian distribution. As it turns out, the entire section on statistics, that is confidence intervals, students' t-tests, Grubbs tests, all this business is rooted in the Gaussian distribution. And the reason why that is the Gaussian distribution is the model that we invoke for considering random error in chemical analysis. This is the basis behind our random error model. The Gaussian distribution is also known as the normal distribution, or else the bell curve distribution. You hear a lot about that when you're talking about grading. So I'm considering it here in this video because I think a good understanding of the Gaussian distribution is in fact critical to understanding those statistical tests that you learned about in your class, or that you will learn about in your class. Alright, so how does this relate to analytical chemistry? You usually think about grades or something of the sort when you talk about the Gaussian distribution, but we can also use it in our chemical measurements, okay, or in measurement science in general. The reason why that is because we're able to make a plot of the frequency with which an observation is observed as a function of measured value. So in this experiment, envision yourself going into lab and measuring something over and over and over and over and over and over and over again. A huge number of replicates. Now you're probably not going to get the same exact measurement every time you do the experiment. Sometimes it'll be a little high, sometimes a little bit low. There will of course be a data set mean. Denote that here at this line. I'll just make up a number. We'll say that the data set mean is equal to 12. Okay? It can be anything. There's no significance to 12. Maybe it's 16, 24, it doesn't matter. Alright, we're just saying that that's the mean. Now it just so happens the most frequent values that you observe in the analysis will lie very close to the mean. So it'll be very popular to get numbers right in through here. The frequency of observation will be high. You'll have a lot of those, okay? But as you go to larger numbers or smaller numbers that are relatively far from the mean, you'll find that the probability or the frequency with which a value is observed will drop off. And likewise, if you get to smaller numbers, further you get from the mean, less likely it will be to see a value. And at some point, if you go to extremes, either extreme low values or extreme high values, it'll be extremely improbable that one of those will come up. They're just too far from the central value. It sort of exceeds the bounds of random error, if you will, okay? Well, this distribution that I just drew here is an example of one of these normal or bell curve distributions. It's symmetrical about the mean. We at least model it that way and hope that that's the case. And this is what you'd find if you go and you do this experiment, say thousands of times. Most frequent values obtained, or most frequent results obtained, would be very close to the mean. And as you got farther from the mean in either direction, either lower or higher values, it would be a lot less improbable. Let's take this data now and replot it to make a more general case, or more general statements. Instead of plotting the x-axis as our measured value, what I'd like to do now over here is plot the frequency of observance, which is the same as what it was over here, more or less, as a function of the standard deviation from the mean. This is the number of standard deviations from the mean. Okay? So if your standard deviation of this data set was equal to 5, if I write plus sigma, that would be the mean plus 5, or the mean minus 5. In this case, this is a minus sigma. Okay? So that would be the mean minus 5. Okay? So I can just basically transpose this axis or change the values on it if I like. Another thing that I'm doing in this discussion that we're going to continue on with now is I'm normalizing my data such that the area under this curve is going to be equal to 1. 1 being representative of the entire data set that was collected, okay? Or the entire population of data is probably a more correct statement, okay? That's going to be important The reason why that's important is because it's going to allow us to determine what fraction of data lies within each of these intervals that we're going to talk about here on our x-axis. And that'll be super important for establishing probabilities, for detecting differences between data sets and things of the sort. Okay, this is basically the basis for that. So again, frequency of observation versus standard deviation from the mean. Now if you look very closely down here on this axis, and maybe I can even zoom in a little bit for you so you can see this a little bit better. I want to focus in on this plot for a second, okay? What you see is I've plotted this axis in standard deviations from the mean. Here's my mean at 0, plus 1 standard deviation, plus 2 standard deviations, plus 3 standard deviations, minus 1 standard deviation, minus 2 standard deviations, and minus 3 standard deviations. The reason why I plotted it like that is because we can actually start to make statements about what fraction of data lies in any one of these intervals. It just so happens that for a Gaussian distribution, if I consider this interval from 0 to plus 1 standard deviations, which I'll try to color in here in red, that area contains about 34.15% of all data points. They should lie in that area. So you see in that area I've got 0.3415 written there. That's the fraction out of 1 of all the data that lies in that little shaded in area between 0 and plus 1 standard deviation. I can extend this between 0 and minus 1 standard deviation if I like. And if I do that, guess what? Another 34.15% of data is there. Or if you want to do it a fraction out of 1, it's 0.3415. So in this area, plus or minus 1 standard deviation from the mean, I can account for a fractional 0.683 of all data points, which also corresponds to 68.3%. So 68.3% of data should lie in that range that's bounded by plus or minus 1 standard deviation. And that's true for the Gaussian distribution. Very significant, okay, because we can start making probability statements of whether or not a data point should be in there. It's about 68% likely, right? But let's extend this range out a little bit further now to plus 2 or minus 2 standard deviations from the mean. I'm going to try to shade that in with this pencil here, okay? I hope you can read the number that I wrote in the box there. It's 0.136 and 0.136. So about 13.6% of all data would lie in this range between minus 1 and minus 2 sigma, and another 13.6% of points would lie in this range. But the beauty of that is if I start adding it all together, if I go to 2 sigma plus or minus, about 95.5%. So 2 sigma encompasses 95.5% of all points. And you remember 1 sigma was 68.3% of data. Okay? I'm writing that here at the bottom. I'll show that to you in a second, okay? I want to focus on this plot for a little bit more. So boy, if we extend our standard deviation range plus or minus 2 from the mean, 2 standard deviations from the mean, almost 96% of data points should lie in that range. And if I'm even more brave, and I extend my range to plus 3 or minus 3, so that's this area in through here, and this area in through here, That's less populous data area. But it turns out about 2.1% of points lie here, and 2.1% of points lie here, because again, it's symmetrical, okay? So if I extend my range all the way out, let me use that pen again. So that broad range of the 3 sigma plus or minus, guess what? 99.7% of all data, or its fractional amount 997.997, will lie in that plus or minus 3 sigma range. So you can see the farther we go away from the central value, the mean, the less likely it is we are to find data. And if I define a range +3 to -3 standard deviations around the mean, only 3 out of 1,000 data points will be outside of that range. So what establishing this Gaussian distribution allows me to do is to start to state the probability with which a given data point belongs to this distribution. If a data point is 6 standard deviations from the mean, it is extremely unlikely that that data point belongs to this distribution. I could try to calculate a probability if I would like to, but it would be extremely unlikely, okay? So all of these tests that we're going to talk about, Grubb's test, student's t-test, determination of confidence intervals, it all comes back to this Gaussian distribution and the fact that certain fractions of data lie in each range, okay? Now, let me zoom back out here. And let's kind of finish this off and talk about things that you're probably going to need to know, or what I'd like you to know. I would like you to be able to have some familiarity with this type of chart that we just talked about here, okay? Understand like what fractions of data are in each standard deviation interval. You should also know this information that I'm writing here at the bottom. This is the total integrated fraction between plus or minus 1 standard deviation. It's about 68.3% of data. For 2 standard deviations range, it's 95.5%. And for 3, it's 99.7% of all data. Also understand that this Gaussian distribution is in fact the basis for our statistical hypothesis testing that we're going to talk about in the statistics portion of the course. Alright, well I hope that you've enjoyed this primer on the Gaussian distribution. I do think it's an important concept, and I hope this video was useful. See you next time.